hope you're doing well. My name is Dallas, and I'm a student of robotics or mathematics or control theory or whatever you want to call it. But today I have something super cool in store for you. And my hope is that whoever you are, engineer, engineering student, mathematician, or a hobbyist who reads math in their free time, my hope is that you get something useful out of this video because I believe that as engineers, it's our responsibility to not only know these mind boggling disciplines, but also know how to teach them and make them digestible for the public good. So, autonomous systems are only as safe as the policies that guide them. But what if your robot or autonomous ground vehicle or autonomous air vehicle, whatever it may be, doesn't know when it's heading towards danger until it's too late? In this series, we'll be exploring something called Hamilton Jacobi reachability. I'm not going to explain the dense theory behind this in this video, so don't worry. We're just going to be using it. But we're going to see how this mathematical wonder gives us powerful tools to filter unsafe behavior before it happens. I first want to thank Kensuke Nakamura of the Carnegie Mellon University Robotics Institute for creating this outstanding Python notebook that walks us through the fundamentals of safety for autonomous systems, and also to Dr. Herbert of the Safety for Autonomous Systems Lab at UCSD for providing me with this notebook so I could explore deeper into this fascinating discipline. So, Kensuke specializes in robust optimal control and generative models to allow robots to safely operate in unstructured and uncertain environments. I thought it would be a really cool thing or I thought it would be a great learning experience to walk through this notebook and extrapolate upon it to create a series of educational videos to show you, the viewer, the basics of what it takes to make an autonomous system safe and robust. So, welcome to episode one. This is safety filtering and multi obstacle safety policies. All right, let's get this party started. We're going to be first talking about theoretical foundations. And the big question here is, what is a safety filter? So, our goal today, again, will be straightforward. We're going to create something called a safety filter using a mathematical method called Hamilton Jacobi reachability. We're going to look at some very interesting three-dimensional constructs, at least three-dimensional in our case here, called backwards reachable tubes. And don't worry about the big words right now. By the end of this video, you'll have a basic understanding of how safety is handled in a simple autonomous system. So without further ado, let's get into it. All right, so in Kensuke's notebook, the first thing we see at the top is that we're importing all these powerful libraries, and I just want to talk briefly about what they are. JAX and JAX.NumPy allow us to do high performance GPU accelerated mathematics. HJ Reachability is a Hamilton Jacobi reachability analysis toolbox, so it's already pre built for us. Super great. Plotly, Matplotlib, animation. If you've worked or done any sort of stuff in this field before, we're going to be using these to visualize these mysterious reachable tubes that we just mentioned. So let's start with the basics here. Say we have a robot or autonomous vehicle, and in order to mathematically model this robot, we decide that we're going to say that it exists in a grid like environment, right? So we've all probably taken algebra at this point. You guys know X, Y, and you can plot points on this grid, right? X equals 2, Y equals 3, right? And we're going to track the robot's X position on the grid and its Y position and its heading, which can be thought of as the direction the robot is facing, right? It's an angle. So this is great. And let's take all this information and put it into a neat little package that we call the state of the robot, right? So we'll say X, this state vector, is equal to Px, Py, and P theta, or just theta, my bad. Now, this is great and all, but the robots and autonomous vehicles move around a lot. So we're more interested in how they change over time, which in engineering is called the dynamics of the system. Now, say our robot follows this set of dynamic equations, right? P dot x equals v cosine theta, P dot y equals v sine theta, and theta dot equals omega. The dot means we're paying attention to the change in this variable, right? So this is the change in the x position, the change in the y position, the change in the direction that we're facing. And we're storing it, we're quantifying it with these quantities on the right side, right? So we're just looking at the change in the x position and it follows these rules. And this is the same for y position and theta. And in the literature, this model is called the 3D Dubin-Carr model. This v here is the robot's linear velocity. And let's say we set it to 0.5 meters per second and we keep it there. So it's fixed. Then say we want to control the robot by changing the direction it faces, right? We can send a command to the robot that changes its direction. So mathematically, we'll call controls u. And in this case, since we're tracking the change in where the robot is facing, called heading, we'll let u equal omega. Or in words, the change in the robot's heading is equal to the angular velocity. And we'll say that the angular velocity, whatever it's equal to, stays within the range of -1 radian per second to 1 radian per second. Great. We have the robot in our mind now. We know how it behaves. Now, this robot is in an environment, and if there are obstacles in that environment, we want to make sure the robot doesn't collide with these obstacles. So, wouldn't it be great if we could tell the robot that it's okay to drive in certain places, but it must stay out of others? Well, we can, but robots don't speak human language. Well, I guess they do now with visual language models, but for simplicity, robots speak math and code. So we'll need to figure out the math here. Say we have some obstacle in our grid environment at 0, 1. We'll define what is known as a failure set around the obstacle. And this failure set contains any state within a 0.5 meter radius circle in the px-py plane, irrespective of the heading angle or the direction the robot's facing. Okay, let's get mathematical. We're going to define something called a signed distance function now. And what is that? So a signed distance function, Lx, is a scalar function that tells you how far a point x is from the boundary of a set. So typically an obstacle or a region of interest is what we want to create this boundary around. If the SDF, we'll call it SDF just for shorthand, so I don't have to keep saying signed distance function, but if this SDF has a positive value, then x, which remember is the state, is outside of the region. If the SDF is 0, it means x is on the boundary of the region of interest. And if x is a negative value, x is inside the region of interest. We'll be repeating this many times throughout the video to make sure you understand how these SDFs operate. Now, we got to introduce the sub-zero level set, which unfortunately, when I learned this, it has nothing to do with Mortal Kombat, but it definitely has a cool name. So what is it? The zero sublevel set, or the sub-zero level set, of Lx is defined mathematically as f equal to x. So all our states within the real numbers or real vectors, don't worry so much about that. But it's all the states where L of x, our SDF, is less than or equal to 0. And in English, this is what we call a failure set or unsafe set. This set includes all states that are in or on the boundary of an obstacle. So anytime Lx is less than or equal to 0, the robot's in danger. This is why we use Lx as a barrier function. It's a sub-zero level set, and it's literally the region we want the robot to never enter. But like we said, when it comes to robotics, you must define things mathematically. So this is how we do it. All right, let's revisit our signed distance function again now that we're a little bit smarter, and let's define it mathematically. We're told that the robot state x equals px, py, and theta. Obstacle 1, we'll say it's centered at 0, 1, and it has a radius of 0.5 meters. It's important to note that the heading of the robot doesn't matter for the obstacle, just its xy position in the environment. So we only care about the position, not the orientation. We define the SDF L of x like this. We'll say L of obstacle 1 at x is equal to the square root of px minus 0 squared plus py minus 1 squared quantity minus 0.5. So now again, let's repeat our fundamentals so we really get this, right? So if this L of x is less than 0, if this equation we just came up with evaluates to something negative, that means the state is inside the circle. If L of x equals 0, it means we're on the edge. And if L of x is greater than 0, it means we're safe. So if you've studied vector-based mathematics before, and even if you haven't, you might notice that this is just the Euclidean distance from px, py to the center of the obstacle minus the radius. Very neat. Okay, so we've looked at the scenario now where there's one obstacle, and we've developed this sign distance function to give us an idea of how far we are from the obstacle to the given robot state. But what if we have two obstacles? Say obstacle 1 is at 0, 1, and obstacle 2 is at, I don't know, let's call it xc, yc, and it also has radius 0.5. Well, now we would need to define two different sign distance functions, right? We would call them L1x, which is the SDF to obstacle 1, and maybe L2 of x, which is the SDF to obstacle 2. But that's a lot to keep track of, right? If we just kept scaling this up with a bunch of obstacles, like we're going to have to keep track of all these functions. And we want a single function that encodes both of these obstacles simultaneously. Well, how about we use a sort of comparison between what these two SDFs give us? So these two functions will evaluate to something and we'll take the minimum of the outputs. And I promise you'll understand why in just a moment, right? But the idea is to take the minimum of the outputs. So mathematically, it's going to look like this, right? We have Lx equal to the minimum of what the two other SDFs give us, the two individuals. So we have the minimum of L1x and L2x. So whatever they output, we take the minimum of it. And we do this because the robot is in danger if it's in either obstacle. The minimum distance to the nearest obstacle mathematically combines our two failure sets. And this means the combined unsafe set is the union of the individual safe sets. So let's go ahead and define it like this, right? It's all the states x such that this combined function L of x is less than or equal to 0. And this is equal to the union of the individuals, right? So on the left, we see x such that L1x is less than or equal to 0, or all the states such that L1x is less than or equal to 0, union all the states such that L2 of x is less than or equal to 0, right? And this, boom, combines everything into one neat little guy. So now we're cooking with gas. We notice that the union of unsafe sets for two failure sets is the same as the unsafe set of the union of two failure sets. And this is actually one of the true-false questions or the true-false claims that Nakamura presents in the paper, and he wants you to think about it. So this was it was an interesting mathematical exercise. So we have the unsafe sets that we modeled as, the unsafe set for L1 and the unsafe set for L2, the places where the SDFs evaluate to something less than or equal to 0 given the state. And their union is this, right? This minimum less than or equal to 0. So, which is exactly the unsafe set of Lx, this big function that we have, this one single function. We're just taking the minimum of L1x and L2x. I'll repeat that 1,000 times till you get it. And indeed, taking the minimum of the SDFs gives us the union of the failure sets. Okay, let's do a checkpoint so we understand where we are. In safety critical robotics, we use this thing called a sign distance function to define what it means to be in danger, right? It's a function that returns a positive number when you're safe, 0 when you're on the edge, and a negative number when you're inside an obstacle. So we define the unsafe region as the sub-zero level set of this function. In this demonstration, our robot operates in a two-dimensional plane, And we define circular obstacles using these signed distance functions. If we want to account for multiple obstacles, we simply take the minimum of their distance functions. That way, the robot is only safe if it's far from all obstacles. That's how we mathematically encode safety into our controller using reachability. And to just really drive the point home now, let's do it again. You have two obstacles. One is near the robot, one is far away. And you ask yourself, how unsafe is the robot right now or currently is? You evaluate L1x and L2x, the sign distance functions to each obstacle, or the sign distances to each obstacle. And suppose L1x gives you negative 0.2 and L2x gives you 2.0. Well, L1x being equal to negative zero point 0.2 means the robot's inside of obstacle 1. L2 of x being equal to 2 means the robot is 2 meters outside of obstacle 2. And then we ask, what should L of x return to represent the danger? Well, if you had these two values and returned the maximum, you'd get 2.0 and falsely believe you're totally safe. But if you take the minimum, L of x equal to negative zero point 0.2, or that's what the minimum would be in this case, this clearly indicates danger. Taking the minimum gives the distance to the nearest obstacle boundary. If any Li of x is less than or equal to 0, then L of x as a whole is less than or equal to 0, and the robot is in or touching at least one failure region. So we take the minimum of all obstacle sign distance functions because we want to evaluate the robot's distance to the nearest obstacle. This is the one it's most likely to violate. If the minimum sign distance is negative, then the robot is already in danger, and even if it's far from all the other obstacles, it's still in danger. That's why we define our overall failure set as the union of the individual ones and use the minimum operation to represent it. Boom. Okay, now let's compute this backwards reachable tube that I keep talking about for the dynamical system we were talking about previously. I'm going to be showing you Nakamura's code and walking you through it, but I have to note, to understand code, you can't just copy it. You've got to go through it line by line so you own it, right? And so we'll be looking at that Dubin's 3D class, reachability dynamics, for our scenario here where we want to find a BRT. We start at the top, and we see that we're using JAX for GPU accelerated computation, like I said before. And this HJ reachability.dynamics gives us a base class that we can extend. And sets helps define control/disturbance spaces like boxes. Here's the robot's constant forward speed. It's hard coded into both the JAX and PyTorch dynamics. And this inherits from a base class that expects dynamics of the form x dot equals f of x plus gx times u plus hx times d, where u is the control input and d is a disturbance like wind, drift, uncertainty, etc. In the initialization method, we see the arguments max turn rate, which are the bounds on our angular velocity omega. We're setting control mode equal to max, so HJ reachability will assume worst case control is trying to maximize the value function. And disturbance mode equals min, so worst case disturbance is trying to minimize the value function. Don't worry about if you don't understand any of this. I'm just walking you through this for the more technically minded. And so hopefully you can pick something up. Okay, here we're going to store speed as an instance variable. And here we're defining the control space, and specifically recall that we're defining u equal to omega, which is bounded by -1 to 1, and that's the angular velocity. All right, here we notice that the disturbance is turned off or 0 everywhere, but the disturbance related methods are still defined in this code, and maybe we'll come back in a future video and play around with these to see how this system behaves with disturbances, but we're not going to worry about that right now. Okay, then we pass all that info to the base class, which handles things like optimization over U and D for reachability. We turn our focus now to the open loop dynamics. This is the drift term in that equation we saw, f of x, and the system evolves like this. So without control input, it moves forward at speed v, and heading doesn't change unless control is applied. Kind of like what we talked about in the previous chapter, right? Or it is what we talked about. Now, this is the control Jacobian g of x, so the second term in that equation we just saw. And this defines g of x equal to 0, 0, 1 transpose, if you will, because control input u equal to omega only affects the heading, right? The theta dot equals omega, like we discussed previously. We move down and we're just going to briefly mention this one because we're not going to use it in this video, like I said, but this is the disturbance Jacobian h of x, which hypothetically models disturbances in x and y only. And notice there's no disturbance in the heading. Okay, now let's talk about part two, which is the Dubin's dynamics tensor, which is a discrete time simulator for the Dubin's car written in PyTorch. This is used for simulating trajectories under some control policy. The current state here is an n by 3 array, and this is a batch of xy thetas, so a batch of states. Action is of size n by 1, and this is a batch of omega values. And this uses a method called Runge-Kutta-4, RK4, to compute the next state. This is something I learned or was briefly mentioned even in my grad level robotics class, but we never dove into it, so don't worry about it. But there's a lot of advanced methods utilized in this notebook that you might be asking yourself, what's the mathematical formulation for HJ reachability or what's Runge-Kutta, but that's not the goal of this video. I can make videos later on these topics if I suddenly feel the need to go through the rigorous derivations for these concepts. But for now, we're just studying a pre-built architecture so we can learn our fundamentals. These are the standard Dubin's car dynamics, which you should recognize by this point. But note that y dot and x dot are reversed in torch dot stack, which just seems like sort of convention, some sort of convention flip or something. I'm not exactly sure. And the Runge-Kutta method we mentioned earlier looks like this. Basically, RK4 estimates the next state more accurately than Euler by evaluating dynamics at 4 intermediate points. All right, lastly, we are wrapping the heading angle here, and this keeps theta in between 0 to 2 pi, so it prevents angle overflow. Now, that was a lot of code, but the idea is this. We define the robot's dynamics using a 3D Dubin's car model, where the robot moves forward at a fixed speed and can turn using angular velocity. The heading changes based on the control input, and we can optionally model disturbances too. We implement this in both JAX for reachability analysis and PyTorch for simulating trajectories. This gives us a fully defined dynamical system we can now analyze for safety using Hamilton-Jacobi reachability. Beautiful. Okay, now we turn our focus to constructing a grid-based BRT solver using HJ reachability, which is the heart of the safety filter. Let's break it down. So here we're instantiating the previously defined Dubin's 3D class, which again models our dynamics of this form. And this is the system for which we will compute the BRT, like I said a couple minutes ago, I believe. Now we're going to define our actual computation grid. So one axis is the x position, which we will bound from -2 to 2 meters. One axis is the y position, which we will also bound from -2 to 2 meters. And a third orthogonal axis is the heading angle theta, which we bound from 0 to 2 pi. We'll define the resolution of our grid as 51 points per dimensions, right, x, y, theta, which will give us a 3D grid. And it's very important that you understand this. More resolution equals better accuracy, but slower compute. Now, this is where we actually construct the computational grid, and it's important to note that periodic dims equal to 2 means theta is periodic. And this means it wraps around at 2 pi, like we said before, which makes sense for a robot heading angle. Okay, awesome. We know the setup for our grid, and now we say, okay, how do we turn our signed distance function Lx that we talked about? We learned about this earlier. How do we turn that from math to code? Well, first, let's define our obstacles, right? That's what we started with. So, this is how we define the second obstacle. They define the second one first here. And notice how it has the same radius as the first obstacle. You'll see in the next line, we just define the first obstacle at 0, 0. It's just hard coded. We just pass it right into this. And go ahead and take a look at this. So, now for both obstacles, we compute their individual sign distance functions, L1x and L2 of x, and grid.states brackets with the little colon 2 in it selects px py across the grid, and subtracting the radius turns Euclidean distance into sign distance. Booyah. Now, here's the challenge. Nakamura left this line blank here for us and challenges us to combine the two distance functions. But recall that we already know how to do this, right? Remember that minimum business of all the sign distance functions and gives the combined danger, and the robot is in danger if it's close to any obstacle. So we're smart now, and we know that our overall sign distance function will be this, right? We're taking the minimum, right? So failure Lx equals JNP dot minimum, and we're going to pass in obstacle 1, obstacle 2, and it's the same thing as what we saw where the two sign distance functions are evaluated and we're taking their minimum. Okay, next is the solver configuration, which configures the HJ solver with very high numerical accuracy and a BRT post processor. So the solution is computed backwards in time. That's the magic of backwards reachable tube. The solution is computed backwards in time and collects all states that could end up in the failure set. So here we set the initial time to 0 and the target time to negative 2.8 because we want to do backwards reachability for 2.8 seconds. What this means is that we're looking at all states from which, within 2.8 seconds, the robot could end up in failure. And now finally, we solve the HJPDE, the Hamilton-Jacobi partial differential equation for the more mathematically inclined. This runs the solver using our Dubin's car model, grid, and the initial unsafe set, and computes the value function that defines the BRT. Now, I want to make a note here that this is what we are actually computing. So I'm going to show you a video of a three-dimensional BRT that I did in a MATLAB version of this Python notebook. And this backwards reachable tube is a three-dimensional representation, at least in the case we're working with, because we're only considering 3 dimensions for our dynamics. But it represents all states from which the robot is guaranteed to hit an obstacle within a few seconds, no matter what the controller does. It's like danger reaching backward through time, warning us where we should not be right now. Okay? So, just like I showed, this BRT is three-dimensional in our case. And so we're going to slice this 3D grid at theta equals to 0 to see what it looks like in 2 dimensions at the heading angle of 0 degrees. The greater than 0 implies that we are plotting the safe region. And because, remember that places that are positive for our sign distance function correspond to safe regions. And we're going to see a top-down view of where it's safe or not in the px-py plane when the heading is 0, when we slice it right there at 0. So without further ado, let's run this code now and see what we get. Okay, let's talk about what we're seeing here. So the yellow regions are the safe areas where the sign distance function L of x is greater than 0, meaning the robot is at least 0.5 meters away from any obstacle. The dark purple regions, or the circles that we see, are the failure sets where L of x is less than or equal to 0. And this means the robot would collide with an obstacle if it entered those regions. So, how does this connect to the math? Well, each dark region corresponds to an obstacle, the ones we define to be centered at 0, 1 and -1, -1. The dark areas are the sub-zero level sets of L of x. And since we defined L of x equal to the minimum between, L1x and L2x, this means each pixel's values corresponds to the distance to the closest obstacle. So the contours of the purple regions represent the edges or danger, and crossing these edges means collision, right? So you might be wondering what these axes mean in this in these plots, because didn't we center our obstacles at 0, 0 and -1, -1? Well, these axes don't seem to match, right? That's because the axes in this plot show grid indices, not physical coordinates. The plot is visualizing a 2D slice of a three-dimensional NumPy array over a discretized grid, not actual XY coordinates. And even though we define our obstacle centers using physical coordinates, our computational grid is indexed, and the plot shows grid indices, not real world values. So we have to map between the two using the grid resolution, and that's why 0, 0 ends up in the middle of the plot, like around like index 25. For clarity, I don't know if this is numerically accurate, but I went ahead and updated the axes to show the robot's position in meters. Now you can clearly see that our obstacles are centered at 0, 0 and -1, -1. And this makes the failure set plot not just a visualization, but like a real world safety map. So you must understand that here we're plotting the original sign distance function slice at theta equals 0. And this shows where the robot would immediately collide if placed at that orientation. It's the true shape of the obstacles in the environment that we translated from the math. And again, it's only the regions where the robot would immediately be in danger if placed there right now at heading theta equals 0. But that's all. It's just the obstacle geometry. And we can think of this like a snapshot of the known danger zones. But there's no dynamics, there's no prediction, there's no forward thinking here. This just answers the question, where is the robot physically overlapping with an obstacle? Okay. Now, next, we're going to look at the plot, or we're going to plot the reachability based safety envelope, which is plotting the value function after running the HJ reachability solver. We need to be clear here, as this is one of the most important distinctions in reachability analysis. We have the raw failure set that we just saw, which is just the obstacle regions, and now we're going to find the backward reachable tube. This shows us where the robot could end up in danger, even if it's currently in a safe looking spot. It accounts for the robot's dynamics, fixed speed, the control limits like the bounded turn rate, and the time horizon that we set to 2.8 seconds. And this is what makes it a powerful safety filter. It includes all states from which the robot will eventually reach failure, even if it's not currently inside the obstacle. This one answers the question, from where could the robot drift into a crash, even if it starts safe? So we saw the raw failure set, which again is the obstacles as defined by geometry. The robot would only crash if it's already inside. But now we see the backward reachable tube. It tells us which states are dynamically unsafe. Even if a state looks safe at first, if the robot can't stop or turn in time, it's already on a crash course. And that's the core idea of a safety filter. It flags risky decisions before it's too late. Okay, so the original BRT is three-dimensional, like we said. Remember, it's position, x, y, and then heading angle would be our third axis. So we're viewing a two-dimensional cross-section here at theta equals 0. And if we sliced at another angle, like theta equals pi, for instance, we might see slightly different contours. Each slice of the 3D reachable tube corresponds to a different heading angle, and since we discretize theta into 51 values from 0 to 2 pi, the 25th slice lines up right in the middle, meaning the robot is facing left, or like the negative x direction, at about pi radians, and right, which is like the positive x direction, at 0 radians. Now you're going to be looking at these plots, and things are a little wonky here, but listen to my words, try to piece it together. And in fact, let's go ahead and plot at two different heading values. Okay, so we're going to run this code here, and we're going to get a comparison between the two BRT plots at these different heading values. So let's take a look at the plots. So this target values colon 0 is the BRT at theta equals to 0, so a heading angle equal to 0. And this is the backward reachable tube slice for when the robot is facing directly right, or whatever that means in this context. It's when theta equals 0 radians, as stated by the code here. The purple danger zones are dynamically unsafe regions, and these are states that will end in failure within 2.8 seconds, even if the robot isn't currently in the obstacle. We see that the BRT is asymmetric, stretching more to the right of each obstacle, and that's because the robot moves forward in the direction it's facing. So if it's pointed toward an obstacle, even from farther away, it's harder to escape. Then in the second plot, we see that the BRT slice for theta equals pi, or we see the BRT for theta equals pi, and this means the robot is now facing left, or like the opposite direction, right? Because this is 0, this is pi, if you're looking at a unit circle. The failure zones are still centered at the obstacles, but the shape of the reachable danger zones has changed. The reachable set now stretches more to the left in the correct orientation of here. I know it goes right and one is left. I sat here for a while trying to figure that out, but the reachable set now stretches more to the left, and this reflects the robot's new orientation. And it's now more likely to enter failure from the left side of the obstacle because it's driving toward it from that direction. So again, it's very important because this confused me at first. Notice how in our figure, theta equals 0 looks like the robot's facing up. That's because in the code, theta equals 0 means positive x, but we labeled the vertical axis as like p of x. But don't let that confuse you. The key point is the BRT shifts depending on which direction the robot is facing, and that's what matters for safety. I was kind of banging my head into a wall trying to figure out if I got this right. So, whether I got this part right or not, the point is that the BRT isn't just a blob around obstacles. It's deeply tied to the robotics or the robot's dynamics. And when the robot faces right, it's more likely to enter failure from the right. When it faces left, the danger shifts with it. This is why we slice the BRT by heading angle so our safety filter can be precise and directional. All right, everyone, that wraps up episode 1 of our safety filtering series. And today we explored how to define safety through sign distance functions. We built multi obstacle failure sets and we computed backward reachable tubes to see not just where the obstacles are, but where the danger lies in the future, all tied directly to our robot's dynamics. The take home message today would be that a safety filter isn't just a static map of obstacles. It's a dynamical prediction tool that tells us which states will eventually lead to failure, and it gives us a proactive way to keep our autonomous systems safe. So, thank you for watching. And if you found this valuable and learned something, please leave a comment. Or if I said something horribly wrong and you want to correct me, please leave a comment sharing your viewpoints so we can all learn as a community. And be sure to tune in for episode 2, where we dive into the next part of Nakamura's Python notebook, which is filtering a nominal policy using real world floor plan data from the Intent Robotics Lab at Carnegie Mellon University. All right, everyone, stay curious, stay safe, and I'll see you in the next video. Peace.